Hi, everyone. This is a paper about parallel derandomization, and it's a joint work with the great Christoph Grunau, who is unfortunately not available to give the talk because of a medical problem. And the focus here is parallel derandomization for Chernoff-like bounds. Parallel randomized algorithms frequently use things like Chernoff bound to show that summation of some random variables is around this expectation, right? And this is so commonly used nowadays, we even have a word for a Chernian bound, right? It has been a long-standing challenge in parallel computation. How can we get deterministic parallel algorithms that have the same properties, right? Or how can we de-randomize these parallel algorithms that rely on strong concentrations like Chernoff bound? To make it a bit more concrete, let's go through a couple of very usual examples. So here are some settings where we use Chernoff-like things. So for instance, I don't know, I have a graph, I want to sample a small set of vertices, and I want that this set has a representative from each large structure. Let's say from a polynomial set of paths, each of them of length, let's say log n over p at least, right? I can sample with probability p and hit each of these paths with high probability, right? Another example is, let's say we want to partition the vertices of the graph into a number of parts, let's say k parts, and I want that when I look at the neighborhood of each given vertex v, its intersection with each of these parts is roughly 1 over k fraction of the size of the neighborhood, right? Or more generally, we often cast our problem as a linear program, right? We get a fractional solution for it, and then we sometimes do randomized rounding to turn this into an integral solution of roughly the same quality, right? And we use concentrations to show that the quality is actually very close to where it was. I'll try to make the discussion concrete with talking about a very simple representation of these problems, which is the discrepancy problem. So let's say we are given a ground set of n elements and a collection of m subsets in it, right? S1, S2, up to Sm. And we would like to partition this ground set into two parts. So this is representing just binary random variables, right? So for each element, I want to decide whether it's in the, let's say, red group or blue group. Okay? And what I would like to have is that when I look at each of the sets, the red and blue parts are roughly of the same size up to a small additive discrepancy. Right? So for instance, this shows such a picture with a small additive discrepancy in each of these sets, right? And one natural way is to just do a random partitioning. This is exactly why I'm talking about discrepancy as a simple representation of randomness, right? And when I just decide for each of these elements randomly, let's say I assign a +1, -1, right? By Chernoff bound, we can see that for each set Si, the difference of the blues and reds, the difference of the +1s and -1s will be roughly root of the set size times a log m. Log m is there to do a union bond over all these m sets. And our question is, how do I get such a solution, such a partition in a deterministic manner, and in particular using a parallel algorithm? Right? Another problem is the lattice approximation problem, which is much more general, and our method applies to it equally, right? And it's a classic problem generalizing the previous thing, right? I put it on the slide. If you're interested, please pause and read, but I don't have the time to go through it. Okay? So what is known about the randomizations of Chernoff, like especially in these settings, let's say discrepancy, right? This is a well-understood problem. Okay. So for instance, for discrepancy problem, right? There's a very old method. It originally was implicit in a work of Erdős and Selfridge, and then made explicit later by Spencer and Rogovan, which in kind of near linear time in the size of the input gets a discrepancy similar to what Chernoff gives, right? And the method is the simple method of conditional probabilities, right? Using pessimistic estimators. What we will do is, we want to fix these +1, -1s of the variables, right? Of these n variables. We do that one by one. And in the course of this process, we maintain kind of an upper bound on the expected number of sets that will have a large discrepancy if we set the rest of the variables just randomly, right? So conditioned on what we have fixed so far, if we set the rest randomly, what would be the expectation, right? We start with a small expectation. Each time we decide the +1, -1 in a way that we don't increase the expectation. So in the end, none of the sets has a large discrepancy, right? Because we started with an expectation less than 1. One has to be careful about how do we maintain this good upper bound, but there's a simple remedy. You do a potential function that mimics the Chernoff bound proof. Please see the book of Allen and Spencer for a nice description. So now, what about parallel derandomizations, right? And I should clarify what I mean by parallel. We work with the standard work depth abstraction, which is, for each given algorithm that I'm considering, there are two parameters. One is the work of the algorithm, which means the total number of computations of this algorithm, right? So that's what the sequential computation always measures, right? And the other is the depth of this algorithm, which is, what's the length of the longest chain of computations that are dependent on each other? Why do we care about these two parameters? Well, you tell me I have P processors. There's a clear lower bound of W divided by P, and there's a lower bound of D for the runtime of this algorithm given P processors. And we can actually match that asymptotically with some scheduling. These are known results, right? So W divided by P plus D is an upper bound. So that's why we work on work and depths. So what's known about parallel derandomization, let's say for discrepancy? This is a very classic topic, has been studied a lot. The most relevant papers for us are this pair of papers from Fox 89 by Motwani, Naor, and by Berger and Rampel. They do kind of a binary search in a k-wise independent space, and they get essentially the right discrepancy. Okay, so S is here just the maximum of the sets. Up to a small loss, S to some small epsilon. The depth is nice, it's polylog n. The problem is that the work is very large. It's actually, large polynomial. And in fact, in the exponent has 1 over epsilon, right? And even if you set epsilon to be half, it's like n to the 5 or so, right? or larger. And the discrepancy itself was later improved. For instance, the most recent work is a work of Harris, right? Gets the right discrepancy, but all of those methods have a very large computational bound, like large polynomials. And the problem with this is that, it means you have a parallel algorithm, but even to beat the speed of single processor computation, I need a large polynomial number of processors, let's say n to the 4, n to the 5, right? This is not a very satisfactory parallel algorithm in some sense, right? So we would like to have algorithms that have work very close to linear, because that's what the sequential algorithm has. And recently, last year, we had a paper that essentially got near linear work and polylogarithmic depths, right? The problem in that solution was that the discrepancy that we could achieve was just barely below linear in the set sizes, set size divided by polylog n. So this is good for a range of applications, but it's far above the, roughly root of set size that Chernoff implies, right? And well, this paper, we get basically what Chernoff has, right? Up to a small constant factor loss in near linear work and polylog depths. So for instance, for discrepancy, we get essentially what Chernoff implies. And perhaps much more importantly, this is a solution for the much wider applicable lattice approximation problem that abstracts many applications of Chernoff bound in parallel computation, and to a special case of it, weighted discrepancy. And in some sense, this gives a generic parallel derandomization for randomized rounding of linear programs. Okay. Let me talk a little bit about some ideas in the method, right? The method is actually, unfortunately, complicated, okay? But I'll try to give some of the base ideas that go into it by way of going through simpler results. So the first result will get discrepancy root of the set size times, instead of root of log m, actually log of m, okay? And we'll do that in depths of computation root of n instead of the ideal polylog n, right? And the second result will optimize the discrepancy bound to the right thing, but we'll have the depth still root of n, right? But the first one will allow me to show you how we set up a recursion for this problem. And the second will allow me to talk about how we control the losses of this recursion. So let's see the first method. So this one is actually very, very simple. Okay, so let's say I have these variables, just 1 to n. Okay, let's partition them in a very naive way into root n parts, each of them of root n variables. Okay. Now I look at each of the parts completely independent of the other parts. Okay, and I have a discrepancy problem in each of these parts. So for instance, in part P1, right, I want from each of the sets, let's say set Si, to get a discrepancy of, the intersection of that set with this part, right? Root of that times a log m, and log m being under the root, right? So this is what Chernoff implies for that part. And that's what we can get for this part with a derandomization, because, each part has only root n variables, right? So in depth root n, I can get that by just basically sequential derandomization, right? Now, the point is that these different parts are solved completely independent of each other, right? Each of them works in depth root n. They're done independent of each other in parallel. So that's in total root n depths for computation, right? Now, could we output just the solution that we get from each of the parts, the whole thing, as the output of the entire problem? No, that's not really possible, because unfortunately, it's possible that for one of the sets, let's say Si, right, it has too many pluses here, too many pluses in this part, too many pluses in this part. It can align all of them in the same direction, right? And then if I look at this set, this discrepancy of it would be just the summation of the discrepancies that it has from different parts. And that can be really bad. That can be up to root n larger than the right bound, right? It can essentially end up being a trivial bound of like n, or set size, right? So that's not really good. So naive mixture is bad. Well, but maybe there's a better way of mixing the solutions from the different parts. And indeed, if we could, for instance, look at this problem as another random problem, we could try to get a random mixture, meaning that, for each of the parts, we could either keep the solution as is or flip all of the solutions of that part, right? With probability half for each of these two cases, right? Meaning that multiplied by +1 - 1 at random, right? If you look into this, right, and see what's the discrepancy that each of the sets gets, it's a very simple analysis. Let me look at discrepancy squared, because that's easier to write. For each set Si, the discrepancy squared of this set will end up being the variance from each of the parts, which is, basically discrepancy of the previous solution, right? So the summation of these variances, right, will be the expectation of this discrepancy squared. And then we will need a log m factor to have a Chernoff bound concentration to union bound over all of the sets I, right? So we end up with a discrepancy, let's say with a discrepancy squared that is S times log of m squared, right? So this gets like, in terms of discrepancy, it's like root of S times a log m on the outside. Now this mixture problem, okay, it's just a problem of finding these root n random variables in a way that we mimic the concentrations of Chernoff for this mixture problem. So this root n variable problem, it's an easier one. We can just do sequential derandomization for it, and that becomes root n depths, right? So root n depths for this part, for this piece of the solution, root n depths for the previous piece of the solution. The whole thing is just root n depths, right? So that covers the first result that I wanted to go through, and kind of shows how we can set up a recursion for this discrepancy problem, right? The only unfortunate thing being that, okay, besides the depths, right, we have a loss in this recursive approach. The discrepancy ended up increasing from root of S times log m to have another root log m loss. And the problem with this thing is that, if I want to go further and further into the recursion, these losses will multiply, and they will multiply in a very bad way, and they will become too large. So the second ingredient that I want to show is, essentially the same depths, right? But let's control the discrepancy and keep it the ideal bound, right? And I want to see how we can do this. Let's quickly have another look at the solution that we just discussed. There were two places that we lost log m when I'm looking at discrepancy squared. One was the solution from each part, right? And one was in the mixture. So each of them was a log of m in the discrepancy squared, right? And I have two of these. That's the problem. If you look at each of these two each of them is optimal for the problem that they're trying to solve, so I cannot avoid that. Some set will have such a loss. So what can we do? Well, this log m loss is actually about the worst case behavior among the sets, right? But if you look at the average behavior, it can be much nicer, right? So for instance, we can enforce this averaging by putting it into the derandomization, basically doing some pairwise derandomization on top of the usual derandomization. And what this means is that, let's say for each part, PT of the problem, I can get the discrepancy squared of each set to be as before, kind of the intersection with that part times log m, right? But we can get that the summation of the discrepancies of different sets, or summation of the discrepancy squares of different sets, is as if there is no loss. It's just summation of the set size intersections with this part, okay? Now, is this averaging good enough? Well, the problem is this is an averaging inside one part, but for different sets, right? But the discrepancy problem doesn't care about the discrepancy of the average of the sets, right? Or the average discrepancy of the sets. It cares about each single set, right? So we have an averaging in kind of a wrong dimension. What we would really want to have is if I zoom in into any single set SI and I look across different parts PT, right? And I average discrepancy squared, that thing should have a small loss. Right? And this is something that, well, we can appeal to our usual friend multivariate weight update to move an averaging from one dimension to the other, right? So concretely in this setting, what we will end up having is that, when dealing with each part, right, we want from that part the discrepancy squared for each set to be as we had before, right? But we want an averaging to also be enforced. In fact, a weighted averaging, which is, for each set, you give me some importance for that set, right? I want that when I sum up these discrepancy squares of the sets with that importance, it should be as if there's no loss. Once you have such a method for each of these parts, then we can actually set up a multivariate weight update. We essentially end up adjusting the importance of each set, in the natural way, based on how much its discrepancy squared has been in this particular part, right? Either increasing the importance proportional to the loss, right? I won't go through the analysis. Many of you are familiar with it. This essentially can end up giving us something like, for each set SI, when I look across different parts, summation of discrepancy squares of the set is as if there was no loss. It's basically just the set size S, okay? And what this implies is that, once I do this mixture problem, right, I get a discrepancy squared, which is, summation of those discrepancy squareds from the parts times a log m. But since the first thing is only S, we get the right discrepancy squared, right? So that's the power of multivariate weight update. It kind of helps us get this summation for each set across different parts. But one has to be careful. This multivariate weight update can only work if the variables coming from different parts are not significantly different. If one of them was very, very large, we would need many, many iterations to get this averaging to work, right? So for this, we need a property from the partition. We need that for each set, these intersections are close enough to each other. Let's say up to constant factor or up to polylog factor, right? So we need a different partition than the naive partition that we had. Well, this itself is a discrepancy problem, right? But we don't need the sharpest bound here. For instance, we can just apply this method that we had in the first paper, in the earlier paper from 2023, right? Just as a black box. And it gives us a partition that for each set, these sizes are roughly close to each other. Okay. Now, this is the solution for root n, right? Also, the multivariate weight update, we will not be able to do it part by part, but we have to batch the parts, but I'll ignore that, right? A second complication is that, when we go into recursion further and further to get the depths to polylog in, we will end up with a partitioning problem that is actually weighted, okay? And there we will need much more properties from this partitioning. much sharper properties. And that's where a bulk of the technicalities in the paper are. I don't have the time to summarize those. Please see the paper for those. So I want to summarize with just a restatement of the result in the paper. We essentially get a resolution for this long-standing problem in parallel derandomization, which is, we get deterministic parallel algorithms with polylogarithmic depths and near linear work, which give us the same guarantees as Chernoff gives in most of the natural settings, for instance, in the discrepancy setting, or in the much more general setting of lattice approximation, which I have summarized on the slide here. Thanks a lot for your attention.